In this video, we will go through several more examples dealing with using calculus to sketch curves. Let's start off with the function x over x plus 1. So the first thing we want to do is think about what is the domain of this function. So the function we are dealing with is x over x plus 1. And this function is defined everywhere that you are not dividing by 0. So in this case, the domain would be, we could simply just say x not equal to minus 1. And then we would like to find the x-intercepts. So we think of x over x plus 1 equals 0. That implies x equals 0. So we have a single x-intercept, 0, 0. For the y-intercept, we think of the value of the function at 0, so f of 0 is 0. So we have the single y-intercept, the same as the x-intercept, which is 0, 0. This function, there is no symmetry. To see that, f of minus x is minus x over minus x plus 1. And the question is, can we write this as f of x, which would make it even, or minus f of x, which would make it odd? And we cannot rewrite it as either of these two quantities. So in this case, there is no symmetry present. Next on our list is to think about asymptotes. So because of the function that we have, it's a rational function, so x over x plus 1. We can see that there is a vertical asymptote whenever the function is undefined because you're dividing by 0. So the vertical asymptote would be x equals minus 1. To find the horizontal asymptote, we think, what is the limit as we approach plus or minus infinity? So if we take the limit as we approach plus or minus infinity and think of our previous techniques, you would say it's a rational function. So it's the same degree in the top and the bottom. So you simply divide their leading coefficients. So that's going to be 1. So the horizontal asymptote in this case is the line y equals 1. So that takes care of the more algebra portion of the problem. Now in terms of calculus, we need to find critical points, intervals of increase, decrease, and classify the critical points. So differentiating via the quotient rule, we get low d high minus high d low all over the bottom squared. And this simplifies very nicely. You have x plus 1 minus x, which is 1, over x plus 1 squared. And this is a different situation for us. Typically, we find critical points. And in this case, if you investigate the function, you have 1, which is never 0, divide it by x plus 1 squared, which is always positive. We can note that f prime of x is greater than 0 everywhere. So that is, for all x. So that tells us that our function will be, there will be no critical points, and it is increasing from minus infinity to minus 1, and minus 1 to infinity. And it would have been okay here to say minus infinity to infinity. I chose to leave out the point minus 1 simply because our function is not defined there. So now on to intervals of concavity. So f double prime x. Well, in order to differentiate this, it's probably best to think of f prime in terms of the chain rule. It's x plus 1 to the minus 2. So when we differentiate that, the chain rule tells us the derivative of the outside function, evaluated at the inside function, multiplied by the derivative of the inside function. So this is minus 2 over the quantity x plus 1 cubed. And if you use the quotient rule, that's exactly where you would have gotten within a few algebra steps. So note once again, this is never equal to 0, but that doesn't mean that it wouldn't change sign somewhere. And the reason I say that is because if you look now at the bottom, x plus 1 cubed, that's something that could be positive or negative, whereas before a square was always positive. So we have to look at where the bottom is undefined, minus 1, and think about the sign of f double prime to either side of it. So if we plug in a number to the left of minus 1, think minus 2, you would have a negative in the top, and you would be dividing by minus 1 cubed, which is also negative. Negative over a negative is a positive. If you were to plug in a number to the right of minus 1, let's say 0, you would have minus 2 over 1 cubed, which is a negative over a positive, so a negative. So our function is concave up to the left of the vertical asymptote and concave down to the right of it. So that would be minus 1 to infinity. So let's put all of this information together and hopefully give a fairly accurate sketch to this curve. So the function we are considering is x over x plus 1. And I've encoded in here, we have the vertical asymptote at x equals minus 1, horizontal asymptote y equals 1, the x and y intercept is a point 0, 0, increasing everywhere, concave up to the left of the asymptote, concave down to the right of the vertical asymptote. So let's first start thinking about what's happening to the right of the vertical asymptote. So we know that our function is going to be increasing, concave down, and go through the origin. So because it's a vertical asymptote at x equals minus 1, as we are approaching it, we must be going to minus infinity. So that would be a curve here that's increasing and concave down. And then as we go off to the right, we are going to continue increasing, concave down, and approach our horizontal asymptote. So the horizontal asymptote is just kind of what the curve goes to for large values. Now, we need to do a similar thing to the left of minus 1, but when I look to the left of minus 1, you kind of see maybe 2 spots to sketch in, and this is where looking at a few key points can work. So for example, if I think maybe minus 2, that might be a good point. F of minus 2 is minus 2 over minus 1, which is positive 2. So we have the point on our curve, minus 2, 2. So our curve passes through minus 2, 2, and in this region we are concave up and increasing. So concave up and increasing. So as we move past minus 2, 2, we're increasing concave up. So we're approaching infinity as we come to the vertical asymptote from the left. And to the left here, we must also be approaching that horizontal asymptote. So this is actually a very accurate sketch of the curve x over x plus 1. Now, note in these problems, the majority of the time spent working on them is when we are gathering the data. So sometimes to get to the heart of the problem, which is combining everything together to sketch the curve, we can just go ahead and give you the data and ask you to sketch such a curve. So we want to sketch a curve that is continuous everywhere and an even function. To say that it's even, recall that means symmetric about the y-axis. So symmetric about the y-axis, which really tells me that I can just sketch what's going on for positive values, and then we will reflect it over the y-axis to get the graph. So we pass through 0, 0, and 1, 2. F prime of x is positive when x is positive. So for positive x values, we are increasing. The second derivative is positive from 0 to 1. So from 0 to 1, we are concave up. The second derivative is negative to the right of 1. So to the right of 1, we are concave down. So because it's even, we're going to sketch what happens for positive x values, and then to complete our graph, we are going to reflect over the y-axis. So starting at the origin, going to the point 1, 2, we're increasing, concave up. But right when we hit that point 1, 2, we continue increasing, but we're now concave down. So to reflect this over, corresponding to the point 1, 2, we're going to have the point -1, 2. So just reflecting this over, we get something like this. And this is a perfect point for me once again to mention that the curves that we sketch, they do not have to be perfect. This is far from perfect. But what we hopefully see here are kind of all of these relevant pieces of information. It looks like an even function, i.e. a reflection about the y-axis. We see where it's increasing, decreasing, concave up.